Okay, well now let's consider problems that we'd like to solve using separation of variables, or where we'd like to use spherical coordinates instead of Cartesian coordinates, okay? So we're going to set this up by looking at Laplace's equation in spherical coordinates, but actually the rest of the treatment will be very analogous to what we've already done. Oh, here, let's look at the outline. So here's the outline that I put up earlier. We're going to consider problems that have spherical symmetry, or at least where we'd like to write the solution in spherical coordinates, okay? So in particular, the spherical coordinates r, theta, and phi, although actually we're going to confine ourselves to problems that have azimuthal symmetry, where nothing in the problem depends on phi. So they'll be kind of two-dimensional problems, and we'll only have to worry about r and theta, okay? We'll start by writing out Laplace's equation in spherical coordinates. And then we'll look for separable solutions where the potential depends on the product of one function that only depends on r, we'll call it the radial function, and one function that depends only on theta, we'll call it the theta function, okay? We'll see that when we do that, that Laplace's equation breaks up into two ordinary differential equations, which we'll then have to solve. Or actually, what we're going to do is look at the solutions, because these problems are very well known and their solutions are well known, even if they're not very well known to us. We'll find that the radial equation, the solutions look like power series in r, the radial coordinate. And for the angular differential equation, we'll find that the solutions look like a set of functions called Legendre polynomials. A set of functions which are very well known, even if they're not very well known to you or I. But in some sense, they're going to function like sine and cosine functions for us. Once we've done this, or taken a look at this, we'll turn to a very simple example, okay? We'll look at the example of a uniformly charged sphere. In essence, we're going to look at an example that's so simple that we know what the answer is, so we'll know if we're doing things right. All right? Okay. Well, here, let's get started. Okay, 1 second. All right. So what kind of problems might we be interested in solving? Well, here are two. In the first one, we have a ball that's made up of two conducting hemispheres. The top hemisphere is set at a potential V0, and the bottom hemisphere is charged to a potential minus V0, okay? And then we imagine there's a thin ring-shaped insulating gap between them. And we'd like to know, what does the potential look inside and outside of a sphere that has this property, all right? It seems like a problem we ought to be able to solve, but, you know, it's not clear how to solve it before we get started. The second problem is interesting too, and it's maybe even more useful. This is the problem of placing a conducting sphere in an otherwise uniform electric field. So we have a uniform electric field, and then we place our conducting sphere into it. And of course, the sphere will disturb the electric field, because the electric field will induce charges on the surface of the sphere, right? Charges rearrange themselves to make the electric field inside the sphere zero, and those locally disturb the electric field. Something like what I've drawn here, okay? So that's an interesting problem, and one that actually has a lot of applications, all right? And both of these problems are also interesting for us because they both have azimuthal symmetry. So that is, nothing in the problem depends on the azimuthal angle phi. The solutions only depend on the radial coordinate and the polar angle theta. Okay, so we can assume azimuthal symmetry. Of course, that's not necessary for solving electrostatics problems, but it makes things quite a bit simpler, and it's how we're going to do things to keep things manageable so that we can understand the new technique we're developing without getting lost too much in the details. You'll see it's hard enough just with these simpler problems, okay? So we're going to end up finding potentials where the potential depends on the radial coordinate and the theta coordinate, but not on the phi coordinate. And as a result, for example, the derivative of the potential with respect to the phi angle will be 0 because the potential doesn't depend on the azimuthal coordinate, excuse me. All right. So in this case, we can write down Laplace's equation as follows. So we'll start out writing del squared V in spherical coordinates, basically following the formula on the inside cover of our textbook. This is 1 over r squared times the second derivative with respect to r of r squared times the derivative with respect to r of v. Excuse me, first derivative with respect to r of r squared times first derivative with respect to r of v. Plus the second term, which is 1 over r squared sine theta, times derivative with respect to theta of sine theta times derivative with respect to theta of v again. Okay? And this has to equal 0. On the inside cover of the book, there's a third term that contains derivatives of v with respect to phi. But since we're confining ourselves to azimuthally symmetric problems where the potential doesn't depend on phi, that term drops out and becomes 0. We're going to look for separable solutions. Solutions that have this form. V of r is equal to one function, the radial function or r function, which only depends on the radial coordinate, times the second function, which we'll call the theta function or the angular function, which only depends on the polar angle. Okay? Now, if I take this separable solution and plug it back into Laplace's equation, things will look like this. Oh, by the way, as I rewrite this, we're going to do one other thing. We're going to multiply both sides of this equation by r squared, all right? And that will get rid of the 1 over r squared terms at the beginning of each term, okay? And since the right-hand side is 0, it doesn't make any other changes. So multiplying by r squared and making the substitution, we have the following. Of course, the theta function doesn't depend on r, so it comes out of the derivatives. So we have theta times derivative with respect to r of r squared times the derivative with respect to r of the radial function. Plus, we have the radial function divided by this sine theta term times the derivative with respect to theta of sine theta times the derivative with respect to theta of the theta function. There we go. And of course, all of this has to equal 0. Just as we did previously, we're going to divide both sides by the potential, which is just the product of the radial function and the theta function. And once we do that, we find that we get the following. 1 over r times derivative with respect to r of r squared, derivative with respect to r of the radial function, plus 1 over theta, or the theta function, times sine theta, times derivative with respect to theta, times sine theta, times derivative with respect to theta again, of the theta function. And of course, this equals 0. There we go. Okay. All right. Now, at this point, we can divide this equation into two ordinary differential equations. And the reason is that each of these equations actually has to equal a constant. Okay? As for the exact same reason that we found when we treated this in Cartesian coordinates. The first term only depends on the radial coordinate r, and the second term only depends on the polar angle theta, but they always have to add up to 0. So that if we fix one of the coordinates, say the polar angle, we can see that the other term, the radial term, has to equal a constant value no matter what r is. Otherwise, the two terms wouldn't add up to 0. And we can make the same argument for the second term. So they both have to be equal to a constant. So this constant, called the separation constant, well, we can write it however we wish. And in this problem, it turns out it's the nicest if we write this as L times L plus 1, okay? So the first term we'll say is equal to L times L plus 1, and the second term then has to be equal to minus L times L plus 1, so that when we add them together, we get 0. Okay? Obviously, we're choosing L times L plus 1 because someone's already done this problem and they found that this gives us a nice, neat-looking answer. And I say, if they've already done it, let's take advantage of their experience, right? And use the same separation constants. Okay. Once we've done that, the differential equation, Laplace's equation, divides into two ordinary differential equations. Okay, the first one is called the radial equation, and it says that derivative with respect to r of r squared times derivative with respect to r of the radial function is equal to L times L plus 1 times the radial function again. That's the radial equation, okay? The second differential equation is the angular equation. And it says, as you've guessed, that the derivative with respect to theta of sine theta times derivative with respect to theta again of the theta function that's equal to minus L times L plus 1 times sine theta times the theta function. Okay? Very good. Here, we'll just put a box around these. Sorry. And then I think we'll stop this video and start looking at the solutions to these equations in the next one. Perfect. So let's pause here.